Good day everyone. We are here to present about Six Sigma concepts, the DMAIC framework, and applications. Our goal today is to help you understand how Six Sigma improves processes and why it's important across different industries. In this presentation, we will show you selected videos that explain the concepts clearly. After each video, we will summarize the important points, so please listen carefully.
What is Six Sigma? Six Sigma is a process improvement method that uses data and statistics to reduce errors in any system. It was first introduced by Motorola and later popularized by General Electric. The goal is to achieve almost perfect process, meaning only 3.4 defects per 1 million opportunities. Why is Six Sigma important? Six Sigma helps businesses by reducing waste, improving customer satisfaction, increasing profits, and making process more efficient. The main idea is to fix problems permanently, not just temporarily.
Let's now watch our first video. The title is Six Sigma in 9 minutes. After the video, our two groupmates will discuss the summary.
Imagine you've been tasked with a really important project at work. The company you're working for produces luxury cars. The production numbers are going down, and a lesser number of cars are getting manufactured each day. There also seems to be an issue with the quality of the windshield wipers that go on these cars. The question you are faced with: is there a way for the company to stop the stall in production and increase the production per day from 1,000 to 2,000? Also, is there a way to find out what's causing the drop in the wiper quality? There is. Six Sigma. Six Sigma gives you the tools and techniques to determine what's making the manufacturing process slow down, how you can eliminate the delays, improve the process, and fix further issues along the way. The concept was introduced in 1980 by Bill Smith while working for Motorola. Since then, Six Sigma has seen worldwide adoption. Six Sigma aims to reduce the time, defects, and variability experienced by processes in an organization. Thanks to Six Sigma, you can produce a defect-free product 99.9996% of the time, allowing only 3.4 errors per 1 million opportunities. Six Sigma also increases customer loyalty towards the brand, improves employee morale, leading to higher productivity. Six Sigma has two major methodologies, DMAIC and DMADV. Let's look at the first methodology. DMAIC is an acronym for Define, Measure, Analyze, Improve, and Control. Let's have a look at each of these stages individually and how it relates to your earlier problem. In the Define phase, you determine what issues you're facing, what your opportunities for improvement are, and what the customer requires of you. Here, you look at the process as a whole and determine the issues with the manufacturing process. In this case, finding out why the cars had varying windshield wiper quality and how to optimize the current process to manufacture more cars. In the Measure phase, you determine how the process is performing currently in its unaltered state. You determine the current number of cars that are manufactured in a day. In the current scenario, 1,000 cars are manufactured in a day, and each of these cars are outfitted with a pair of windshield wipers by one of 30 machines used. Some of the metrics measured are how many cars are produced in a day, time taken to assemble a car, how many windshield wipers were attached in a day, time that takes them to do so, defects detected from each machine on assembly completion, and so on. Following this, in the Analyze phase, you determine what caused the defect or variation. On analyzing previous data, you find out that one of the machines that installed the windshield wiper was not performing as well as it was supposed to. Production was taking longer since the car chassis was being moved across the different locations slower, as cranes had to individually pick and drop the frame. This was because the wheels were attached to the car only in the last stage. Next, in the Improve phase, you make changes to the manufacturing process and ensure the defects are addressed. You replace the faulty machines that installed the windshield wiper with another one. You also find a way to save time by attaching wheels on the frame in the initial stages of the manufacturing process, unlike how it was done earlier. Now, the car can be moved across the assembly area faster. And finally, in the control phase, you make regular adjustments to control new processes and future performance. Based on the changes made, the company was able to reduce production time and manufacture about 2,000 cars a day with a higher quality of output. DMAIC is one of the most commonly used methodologies in the world. It focuses on improving the existing products of the organization. The second methodology is DMADV, which is short for Define, Measure, Analyze, Design, and Verify. It is used when the company has to create a new product or service from scratch. It is also called DFSS, or Design for Six Sigma. Let's take the scenario where the company decides to build a new model, a sports car. In the Define phase, you define the requirements of the customer. Based on inputs from customers, historical data, industry research, you determine what you need to ensure your car becomes a success. The data collected indicates customers are drawn to cars which can achieve more than 150 miles per hour. Customers are also more inclined towards cars which have V6 engines and an aerodynamic frame. Then, in the measure phase, you use the customer's requirements to create a specification. This specification helps define the product in a measurable method, so that data can be collected and compared with specific requirements. Some of the major specifications that you focus on are the top speed, engine type, and type of frame. In the Analyze phase, you analyze the product to determine whether there are better ways to achieve the desired results. Areas of improvement are determined and tested. Based on the analysis of the prototype created in this phase, you find that the product satisfies just about all of the customer requirements, except the top speed. So, research begins on an aluminum alloy that could possibly meet the speed requirements of the customer. Following this, the design phase. Based on the learnings from the analysis phase, the new process or product is designed. Revisions are made to the model, and the car is manufactured with the new material. The analysis phase is repeated based on the new design. You also bring a focus group and see how they receive it. Based on their feedback, further changes are made. And finally, in the verify phase, you check whether the end result meets or exceeds customer requirements. Once you launch your brand new sports car, you collect customer feedback and incorporate it into future designs. And guess what? Your customers are loving the new design. And that is DMADV for you. Six Sigma has also found success in a number of different industries. The petrochemical, healthcare, banking, government, and software are some of the industries that have utilized the concepts of Six Sigma to achieve their business goals. Another commonly used methodology adopted by companies around the world is Lean. Lean is a methodology that aims to remove any part of the process that does not bring value to the customer. It means doing more with less while doing it better. The philosophy behind Lean comes from the Japanese manufacturing industry by Bob Hartman, who at the time was part of Toyota. Since then, across the world, services and manufacturing organizations have incorporated Lean within their businesses. But what if you could have the best of both worlds? A combination of both Six Sigma and Lean. That's Lean Six Sigma. Before we get into Lean Six Sigma, we've got a quiz for you. What methodology is used by companies when they want to release a new product created from scratch? A. Design, measure, analyze, define, verify. B. Define, measure, analyze, design, verify. C. Demand, measure, analyze, improve, control. D. Define, measure, analyze, improve, control. Leave your answers in the comments section below for a chance to be one of 3 people to win an Amazon voucher. Now, let's get back to Lean Six Sigma. Lean Six Sigma is a methodology that focuses on eliminating problems, removing inefficiencies and waste, while improving the working conditions to ensure the customer's needs are better satisfied. It combines the tools, methods, and principles of Lean and Six Sigma. We'll have another video detailing the process of Lean Six Sigma very soon. We hope you found this informative and helpful. If you enjoyed this video, please like and share it. And don't forget to subscribe to the Simply Learn channel. Thank you for watching, and stay tuned for more from Simply Learn.
The video explained that Six Sigma is the main about reducing process variation and improving quality. They introduced the idea of measuring errors using defects per million opportunities.
It also showed that Six Sigma has different belt levels such as white belt, yellow belt, green belt, black belt, and master black belt, depending on your level of training and experience.
So what is DMAIC? DMAIC is the problem-solving framework used in Six Sigma projects. It stands for Define, Measure, Analyze, Improve, and Control. It gives teams a step-by-step method to fix problems effectively. Next, we will play a video titled The Basics of Six Sigma and DMAIC Framework. After watching, two of our members will summarize it.
PySDEC Institute.
Today, decades after it was introduced, thousands of organizations of all types from all over the world use Six Sigma to improve their operations. In this lesson, you'll learn the factors that account for this amazing longevity and success. This lesson will provide an overview of Six Sigma, including where Six Sigma originated and why the originators decided to use Six Sigma in the first place. You will also learn what makes Six Sigma so successful, how Six Sigma helps you make sense of huge amounts of information that come at you constantly, and the limitations of Six Sigma. Six Sigma creates institutional change at a rapid rate, and as a Six Sigma belt, you will be at the center of the change. You'll learn how to help your organization adjust to the rapid rate of change caused by Six Sigma.
There are three common answers to the question, what is Six Sigma? Six Sigma is a metric used to compare process variation to customer requirements. Statisticians use Six Sigma to measure the variability in a data set. You'll learn how to calculate sigma later in this course. Six Sigma measures the process variability by how many sigmas there are between the process mean and the nearest customer requirement. The goal of Six Sigma is a process with only 3.4 errors per million opportunities. Prior to Six Sigma, world-class performance allowed many thousands of errors per million opportunities. Six Sigma is also a philosophy that relentlessly pursues perfection in operations. Six Sigma is a methodology that provides a framework for applying proven principles, tools, and techniques. The technology used in Six Sigma was around long before Six Sigma came along. But Six Sigma put it to use in new and more effective ways. Six Sigma was originally invented by Motorola Corporation to address its quality problems. When a Japanese firm took over ownership of Motorola's Quasar factory in Chicago, they found the quality levels to be abysmal. A year later, they had drastically reduced defects. They did this without changing employees, equipment, suppliers, or designs. All they changed was the way the factory was managed. This was a lesson that many American businesses took to heart as they watched foreign competition steal their customers. Six Sigma was a response to lessons such as this. It was a survival response. Six Sigma came into existence in 1986 at Motorola. By 1988, Motorola won the first Malcolm Baldrige National Quality Award and the rest of the world became aware of the existence of Six Sigma. Research has shown that quality levels are linked to costs. Costs rise exponentially as quality declines. This graphic shows that companies with quality at a 3 or 4 sigma level spend between 15 and 25% of their sales dollars on cost of poor quality. Companies with quality levels near Six Sigma spend less than 5%. Since costs of poor quality are all non-value added, the benefits go straight to the bottom line. This is an important distinction between Six Sigma and the mindless cost-cutting programs that cut value instead of waste. Here's another way of looking at the relationship between Sigma levels and quality. The bottom axis shows the process Sigma level. The vertical axis shows the errors per million opportunities. Error rates drop dramatically as processes become more consistent. Since errors cost money, either in lost customer revenues or in replacement and repair costs, or both. This graph explains why the cost of poor quality and Sigma levels are so closely related. Six Sigma is a rigorous way to manage business processes. It is based on Aristotle's logic and Galileo's experimental method, combined with modern computer power. Six Sigma is all about identifying the root causes of outcomes. It proceeds step by step, testing assumptions as it goes, rather than accepting someone's intuition. The Six Sigma approach begins with an opportunity, either a problem or some potential benefit. This is a result that we either want to create or prevent. To do either, we must understand the cause of the result. We create hypotheses or theories about what the causes might be. The theories give us predictions. Then we collect data to see if our theories did a good job of predicting the results. We refine our theories until the predictions are good enough to form a basis for taking action. When this is the case, we take action to improve the process. The Six Sigma process is sometimes shown mathematically as a transfer function. Y equals f of x. Y is an effect. The x's are causes. The f is a transfer function that relates the two. After you've been doing Six Sigma for a while, you will learn something amazing. A lot of things that everyone is quite sure about will turn out to be false. At this point, you will find that you can never return to the old-fashioned hip-shot management methods. In Six Sigma, we abandon the idea that an organization can be run solely for the benefit of any one stakeholder group. It's not this group or that group. It's this group and that group. Six Sigma identifies the harmony of interests among the stakeholders and helps the leader balance outcomes so that every stakeholder group is satisfied. Six Sigma is not academic research. It is about doing things smarter. As a Six Sigma belt, you need to move deliberately through the 5 steps of define, measure, analyze, improve, and control, avoiding the temptation to get stuck in the analyze phase in a pointless quest for certainty. Get enough information to make an informed decision, then make the decision and move on. Six Sigma works well because the organizations doing Six Sigma create an infrastructure devoted to change. This includes the full-time change agents, black belts, part-time green belt change agents, sponsors, process owners, and champions. The leaders of Six Sigma organizations often change compensation and incentive packages to support change. Obviously, all of this costs a lot of money. To be sure that the investment pays off, Six Sigma organizations carefully monitor the benefits of Six Sigma. Finance and accounting usually plays the major role in setting this up. When you understand how cause and effect works, and how causes are usually interrelated, you'll see that a few big drivers dominate. Six Sigma helps the leaders focus on the critical few drivers responsible for the key outcomes. Six Sigma will provide you with the tools that help you identify and validate these drivers, and then drill down even further until you determine the root causes that affect the drivers. The leaders of Six Sigma organizations use Six Sigma strategically. They create dashboards that show metrics which are critical to the organization's success. Then use these dashboards to identify high-impact, long-term Six Sigma projects. The dashboards also show non-strategic metrics that are dangerously non-competitive. Short-term Six Sigma projects are undertaken to correct these situations. The balance of short and long-term needs is a hallmark of well-run Six Sigma organizations. You've probably heard of information overload. I/O is the result of having too much data to think about. I/O causes many employee problems, and these problems lead to delayed decisions and increased costs. The cause of I/O is the lack of a framework for making sense of the data. Six Sigma provides this framework. Each time you do a Six Sigma project, you will systematically build a model that links dozens of root causes to a few key drivers of a small number of important outcomes. Everyone in the organization will benefit from the deep understanding of cause and effect that you provide. Knowing which few buttons to push to make things happen will provide tremendous peace of mind to your leaders and managers. The costs and benefits of Six Sigma must be tracked. It isn't necessary to get to the penny accuracy, but you need enough information to prove that Six Sigma is worth what it costs. Six Sigma is not a panacea. It provides benefits whenever you are trying to improve an organizational process and where the path to process improvement is unclear. In other words, where the causes of improvement are unknown, Six Sigma can be used to help identify them.
I believe that some things don't lend themselves to being managed as a process, and Six Sigma shouldn't be used for these things. For example, in pure research, discoveries are made in ways that are not well understood, and they're unpredictable. If you try to make these processes predictable, there's a good chance you'll end up destroying the creative process.
Keep in mind that no organization can succeed solely by improving its processes. There are many other things that need to be done, such as staying close to the customer, understanding the competition, being creative, etc. As a Six Sigma belt, you will become an expert at using data to dethrone widely held myths. But don't be too quick to accept the data at face value. Think about why the data show what they show. For example, if data indicate that customers on hold for 1 hour are as satisfied as those whose calls are answered immediately, perhaps it's because the customers unhappy about holding have already hung up the phone and were not surveyed. In Six Sigma organizations, change is the norm. Changes are made before something happens that makes it obvious to everyone that change is needed. This is very different than a traditional organization, where change is usually avoided until absolutely necessary. Six Sigma organizations are constantly looking for things to change. Six Sigma organizations employ people whose job it is to make changes. Some of these change agents have day jobs, while others do it full-time. People generally react to the uncertainty that change brings about by being fearful. They will have many questions. Will I still have a job? Will I be able to do the new work? Will I receive training? Will my pay be affected? The only way to reassure people is with constant communication, and by consistently keeping all of your promises. Six Sigma uses a simple framework for pursuing improvement. First, an opportunity is defined. Next, we measure the process baseline and validate the measurement system. Then, we analyze the process to determine how we can improve it. Finally, we lock in the changes by devising and implementing effective control systems. Let's look at an example of DMAIC. Define the goals of the improvement activity. The leadership identified an opportunity, customer complaints. This is a why that is driven by assembly delays, which is driven by test failures, which is driven by solder defects. We could keep going, but the black belt decided to undertake a project to reduce customer complaints by reducing wave solder defects. Next, measure the existing system. The baseline wave solder defect rate was 5%. In Six Sigma, we don't use percent very often, but we translate the error rates to errors per million opportunities. 5% translates to 50,000 errors per million opportunities. This equates to a process sigma level of 3.1. The measurement system for this project was visual inspection, and the black belt confirmed that the inspector's classifications were reliable and accurate. Now analyze the system to identify ways to eliminate the gap between the current performance of the system or process and the desired goal. The team drilled down on solder defects and found the top 3 drivers. Additional analysis, using statistical and non-statistical methods, determined that maintenance problems, failure to follow procedures, and process settings were root causes. Now improve the system. This involved maintenance, training, and statistically designed experiments to determine optimum process settings. Pilot studies showed that the goal was exceeded and that the improvements in quality also improved other process measurements. Most important, the preliminary results showed that the process changes would greatly improve the top-level why that the project team was solving for. Finally, control the new system. The team changed the preventative maintenance schedule and the manufacturing planning. They also developed new process audit procedures, implemented statistical process controls on key process indicators, and changed the ways new employees were trained. That was a ground-level look at DMAIC. Here's a 10,000-foot perspective on the DMAIC framework. We start with an important opportunity. Then define a project to pursue it. A defined project includes the business case, determination of the project's customer, the key outcomes for the opportunity this project will address, a statement of what is inside and outside the scope of the project, a description of the new process, product, or service the project will create, and a detailed timetable for the project. No definition is operational without a way to measure it. So that's our next step. What are the critical drivers? Do we have sufficient data to measure outcomes and drivers? Are the numbers trustworthy? What is the current state? Can we measure progress and success? Next, we analyze cause and effect. Our goal is to identify, very rigorously, the root causes driving the outcomes. We start by a close examination of the current process to see if there are any special causes of variation that can be eliminated. We build mathematical and computer models to determine what changes need to be made to meet our goals. Then we use our new cause and effect knowledge to improve the process by planning and implementing changes. Finally, we develop control systems that lock in the changes and maintain the improvements. The cycle is then repeated with the next project. Here's an excerpt from the Six Sigma Handbook that shows the different tools to consider during each phase of the DMAIC cycle. It is included as part of your reading assignment too. We are showing here so that you can get an idea that the DMAIC cycle is supported by a good set of technologies and tools that are going to help you as a black belt really pursue the project successfully. You have reached the end of this lesson.
In the video, they explain each step of the DMAIC. Define, understand the problem, and set the project goals. Measure, collect data to know where you currently stand. Then, analyze is finding out root cause of the issue. Improve means creating testing solutions, and control is making sure the solutions continue working over time.
Real-life application of Six Sigma. Six Sigma isn't only for factories. It's used in different industries like manufacturing, reducing defects in production, healthcare, improving patient care and safety, IT service, speeding up service delivery. Big companies like General Electric, Samsung, and Ford have saved millions through Six Sigma.
For the last video, we'll show a real project that used the full DMAIC process. It's titled Learn Six Sigma Project Example with DMAIC. After this, three of our members will summarize the key points.
How can the Lean Six Sigma body of knowledge be applied to a real project? Here's a simple example illustrating the Lean Six Sigma project cycle from start to finish. It is informed by countless projects submitted here at SSGI over the years. To structure the project, we follow the DMAIC framework. It includes 5 phases: define, measure, improve, analyze, and control. First, we turn to the define phase. The problem statement. The Evercool company manufactures and distributes commercial air conditioning units as well as provides existing customers with replacement parts for units in need of repair. Customers have increasingly complained that the time to receive these parts is long. Several have gone weeks without them. A Lean Six Sigma project has been approved at Evercool to study this problem and determine how the order fulfillment cycle for replacement parts can be shortened. The project goal is to reduce the time from customer orders to delivery by 30%. A project charter is a statement of a project's goals, scope, timeline, and participants. The Evercool goal just expressed is a 30% improvement in the fulfillment cycle. The charter also expresses scope, what needs to be done and what does not. For example, the order cycle for new air conditioners will not be addressed. The timeline is 3 months. Finally, an interdisciplinary team of 3 staff has been assigned to the project. Next is the measure phase. SIPOC diagram. We begin with a SIPOC diagram shown below. It helps us identify all suppliers, inputs, process steps, outputs, and customers before proceeding with the project. Further, it assures that no variables have been left ignored. Cost of poor quality. The cost of poor quality, COPQ, defines the economic consequences of failing to meet process goals or customer expectations. In this example, COPQ can be measured in part by estimating the costs associated with failing to fulfill orders within a reasonable period. Indeed, poor quality almost always incurs costs. They can be traced internally to the organization, such as scrap and rework, or they can be traced externally, such as customers taking their business elsewhere. Benefits and costs. Projects need to justify themselves by delivering benefits in excess of their cost. Here is how we could estimate the benefits of this project. The marketing department estimates that Evercool loses an average of 3 customers every month due to poor service. These accounts average $40,000 per year. So COPQ is 3 times 12 times 40,000, or 1,440,000 in lost revenue per year. The finance department, on the other hand, estimates that this represents a loss of about $200,000 in profits per year. By shortening the cycle, it has been estimated that at least half of this amount could be saved, or $100,000 per year. 3 staff will be assigned part-time to the project for 3 months at a cost of $50,000. In addition, the cost of IT changes have been estimated to be $40,000. Comparing the benefit of $100,000 with the cost of $90,000, the benefits in 1 year exceed the cost. Data collection. Data collection is an important part of the measurement phase. Since fulfillment time is the primary focus, collecting data on the length of time between placing and filling an order needs to be collected. The table below summarizes average lead times over a 15-week period. For example, the average lead time for week 1 is 8 days and week 2 is 11 days. Bar charts. Bar charts are very helpful in uncovering the root cause of a problem. Here is how one can prove useful in the Evercool project. First, the possible categories that can explain the delays are identified, and then frequency data is collected for each. These categories start with supplier-related issues and end with transportation issues from suppliers. The second column shows the frequency with which these categories have been observed over a 1-month period. Finally, a bar chart is constructed. As you can see, each bar represents a category, and the height of the bar represents the frequency associated with that category. Also notice that the bars have been ordered with the highest frequency on the left and the lowest on the right. This is called an ordered bar chart. Process mapping. But data is not enough. It also is important to understand the flow of steps between receipt and shipment of the order. To do this, a value stream map, or VSM, is created. Next is the analyze phase. Root cause analysis. In root cause analysis, we attempt to determine the real cause of a problem. So we try to move past a simple explanation that might focus only on symptoms. As you can imagine, solving the symptom is unlikely to have a meaningful or long-lasting result. 2 tools are helpful in root cause analysis: Pareto charts and fishbone or Ishikawa diagrams. Here we will focus on a Pareto chart. A Pareto chart is a variation of the histogram. In addition to identifying the magnitude of the problem, or in this situation, the frequency associated with each category, the Pareto chart also displays the cumulative contribution associated with solving more than one problem. So the Pareto chart might indicate that by addressing the top 3 problems, 83% of the total problem may be resolved. Here is how we can interpret the right-hand vertical axis. If supplier-related issues can be resolved, about 40% of the fulfillment delay can be addressed, and about 65% of the delay can be addressed if supplier-related and quality issues are resolved. Gemba Walk. A Gemba Walk is a workplace walkthrough whose objective is to observe processes, employees, trouble spots, and bottlenecks. They become candidates for process improvement. So this walk is another strategy for uncovering process inefficiencies and observing the possible reasons behind these delays. In this example, the Evercool team would walk through the entire fulfillment process, thereby gaining first-hand knowledge that could be instrumental in continuing to make sense of the data that has been collected. Process capability. The concept of process capability compares what the customer expects to the capabilities of the process. If the process easily meets customer expectations, its capability is high, while if it is incapable of meeting them, it is low. When we start a Lean Six Sigma project, process capability is usually low, but after the process has been analyzed and improved, it should be higher. So process capability can be used both at the early stages of a project to underscore the need for process improvement, and again at the end to confirm that the efforts made have been successful. In Six Sigma, there is a formal way to express process capability. Process capability, CP, measures how close a process is running to its specification limits relative to its natural variability. These specification limits reflect customer expectations, which are compared to the natural variability associated with delivering customer results. The larger the value of CP, the less likely process output will fail to meet customer expectations, called upper and lower specification limits. At the end of the Evercool project and after sufficient data has been collected, we would expect CP to be larger than 1. 5 whys. Repeatedly asking why can help uncover the layers that can lead to a better understanding of the problem. It is another step in getting to the root of the problem. In Lean Six Sigma, it is tradition to ask 5 why questions, and each probing deeper to find the real or root cause of the problem. Here are 5 questions that can be asked in the Evercool project. Why is there a delay in the fulfillment process? Why are orders taking so long to process? Why are there backlogs? Why are we unable to clear backlogs? Why is there no procedure to deal with these delays? Data analysis. Data is important, but raw data is not enough. It needs to be analyzed in a systematic way, which often requires the use of statistics. So we might, for example, compute the average fulfillment times reported previously. That average is 8.67 days. It represents the central tendency of the data. We can also use more advanced statistical analysis, such as regression correlation or hypothesis testing, to learn more about the data. Data is also critical for comparing old and new ways. It avoids ambiguous comparisons, such as, the improvement process does seem to be working, or the fulfillment process is a bit faster. Indeed, when data is used, we can be more explicit. The fulfillment process has improved by 12%. Analyzing other data. However, the analysis phase is not limited to the use of statistics. It also involves analyzing value stream maps, the knowledge gained from Gemba walks, answers to the 5 whys, or data displayed in a Pareto chart. It all helps when analyzing a problem and learning as much as possible about it. Improve phase. Next, we turn to the improve phase. Eliminate non-value added steps. Armed with the insight gained during the analysis phase, the next step is improvement. Non-value added steps are eliminated to the extent possible. Delays, errors, and waste are addressed. Even value added steps are explored to determine if they could be made more efficient. Fumiya and Poka-yoke. One way to address many of these alternatives is to schedule a brainstorming session attended by relevant stakeholders, during which time All of these possibilities for improvement are discussed. Their input can be instrumental in motivating change and limiting resistance that often interferes with what has to be done. During the brainstorming session, it might be useful to rely on FMEA and Poka-yoke. Failure mode and effects analysis, FMEA, involves the staff anticipating problems before any changes are implemented and then taking steps to avoid these problems. In Poka-yoke, staff consider ways to prevent future errors. Pilot testing. Pilot testing can also be used during the improve phase. It can make sense to implement small-scale improvements and then use the results to prepare for the implementation of the full-scale version. Resistance to change. The improvement stage is often accompanied by training. It familiarizes those affected by the change to the new ways. At this point, resistance from those affected by the change often emerges. As a result, it helps when the team has some familiarity with the concepts of change management. Nonetheless, they must at least be sensitive to the reluctance of those affected by the change to adapt to new methods and procedures. Comparing old and new. Has the project been successful? At this point, it is important to compare the new system with the old. In our example, the average time between order placement and delivery was reduced from 8.67 days to 6 days. This is clearly an improvement that has exceeded project goals. Yes, it has been successful. A more formal and more convincing way of comparing the two is hypothesis testing. This statistical test determines if there is a significant difference between the two approaches or if the differences can be attributed to the inherent variability that occurs in all processes. Control phase. Finally, we have the control phase. Outputs change over time, so establishing a monitoring and control system to ensure that this does not happen is a critically important step in a Lean Six Sigma project. Indeed, any project that fails to create a monitoring and control system is a project that has not yet been finished. Control charts are at the center of the monitoring and control function. While the statistics behind these charts can be quite complex, the basic concept is simple. Samples are periodically taken from a process. The sample mean is plotted on a chart, and as long as they remain within specific boundaries, the process is considered to be in control. In constructing the control chart, we use the long-term average output as the target. The upper boundary is called the upper control limit, and the lower boundary is the lower control limit. Here is a control chart for the Evercool case. Notice that the sample means in this example are within the upper and lower control limits, so the process can be considered under control. While this example required a simple X-bar chart because we were monitoring process means, other charts might also be used. For example, a P chart would be used if we were monitoring process percentages, such as the percentage of customers who complain about customer service. Control plan. A control plan goes one step beyond the control chart. It takes the 30,000-foot view and focuses on managing the entire quality control process. As such, it goes beyond establishing quality control charts. It identifies the process owners responsible for the process, as well as the corrective actions that should be taken when an out-of-control signal is observed. The outcome is a formal control plan. That's it. This is a very brief introduction to the way we would organize and manage a Lean Six Sigma project. While your project may involve other tools and is likely to go into greater statistical depth, the basic format and direction described here can guide almost any Lean Six Sigma project. To recap the basic issues of a Lean Six Sigma study, follow a framework, clearly define the problem, measure the problem parameters by collecting data, analyze the data with such tools as Pareto charts and value stream maps. Improve the problem and control the process such that it continues to meet goals. For a full range of courses, from Yellow to Master Black Belt, as well as courses that focus on operational excellence, management, and leadership, visit us at SixSigmaGlobalInstitute.com. Thanks for watching.
In the video, they show how a company followed DMAIC to fix a process that was slow and costly.
They used data to analyze the root cause, create improvements, and made sure the process stayed fixed through controlled plans.
Because of the project, they reduced the processing time significantly and saved a lot of operational costs.
Thank you very much for your attention. We hope you now understand how Six Sigma and the DMAIC framework can help businesses solve problems and improve performance.